All right, well, welcome back to another discussion in calculus, and in fact, a new chapter in calculus. So we're moving out of chapter 7 and 8, which is applications and techniques of integration. We've been working a lot with continuous functions on the real line. This is kind of the name of the game so far with calculus. And we're going to move away. We're going to kind of make a transition. In that chapter 9, we move away from continuous functions and we begin a discussion on discrete functions, functions that are nice and smooth curves in the plane, and calculus the calculus we know might break down. And so we're going to explore these types of functions, and we're going to use calculus and the techniques that we've learned along the way to try to bring these types of functions into what we know, into calculus. And so we're going to be looking at sequences and series, their counterpart. They're one and the same in part. Sequences is the function, and series is the thing you do a lot of times with sequences. You add up the terms of the sequence, and we call that a series. So we don't want to get confused between the two. First, we'll just introduce a sequence. That's going to be just a function, a certain type of function with a restricted domain. And once we define sequences, we work with sequences a little bit. We'll talk a little bit about how calculus comes in with sequences. There's something we can ask ourselves, and then we'll move into the majority of chapter 9, which is going to be about series, is taking these functions, these sequences, and asking ourselves, okay, what's going to happen if we add up all the terms of this sequence? And what we're going to see as well, there's going to be infinitely many terms, and that's now going to require some calculus and some knowledge of how can we possibly add up infinitely many objects. And that's where calculus comes in. All right, so we're going to begin in chapter 9, 9.1. where we are going to introduce a sequence. Now, sequences aren't necessarily a new topic in terms of mathematics. They're introduced in pre-calculus and probably even before this in some algebra classes. You talk about them a little bit, but we're going to remind ourselves, we're going to bring them into the context of calculus and reintroduce them here. And so what is a sequence? If I could best define it for you, it is a function whose domain is the set of natural numbers. So a function whose domain is the set of natural numbers. So we have to remind ourselves, what are the natural numbers? These are our counting numbers. So 1, 2, 3, 4. And so oftentimes we use this kind of bold-faced n-looking thing for the natural numbers. Remember, the natural numbers are just your counting numbers. The important thing to note about the natural numbers is that there is a definitive starting natural number, 1. 1 is the first natural number. Why do I bring this up? Because functions on the real line, or with a real continuous variable, functions we're used to, you have all numbers from negative infinity to infinity, possibly. Right? There's no starting point. The other thing to notice about the natural numbers, though, is they also don't end. Right? We can count forever, so 4, 5, 6, 7. There's no need to stop. So the domain is infinite. It is an infinite set, but it does have a definitive starting point. Those are my natural numbers. And then just remember what we mean by domain. Domain is the input of the function. Okay, so it's what I'm allowed to plug into the function. It doesn't say anything about what the output has to be. The outputs of sequences can be real numbers, irrational, rational. It doesn't matter what the output is. It's just important the input of the sequence is the natural numbers, what I'm plugging in. And so since we're introducing a new type of function, we have some sort of restricted domain. We're going to change our notation. We're used to f and g and h, right? This function notation, f of x, g of x, h of x for functions. We're going to move away from that slightly. Instead of x, we're going to use n for a variable, very natural choice for the natural number. So n instead of x. And instead of f of x, g of x, h of x, we're going to use a sub n. We're going to use subscript notation and the first letters in the alphabet. And so just a matter of notation, we're going to oftentimes talk about sequences. They're going to look like this, dot, 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 where n is my variable instead of x. And instead of f of x, g of x, h of x, we're going to have a n, b n, c n. Now, the outputs of a sequence are called the terms. So just getting some definitions out of the way. So the outputs of a sequence are called the terms of the sequence. And so you'll oftentimes, when we first introduce sequences, you'll be asked, okay, what are the first 5 terms of the sequence? And the terms mean the output, so what are the first 5 outputs of the sequence? And it's not ambiguous for me to say first 5, because there is a definitive starting place, right? We have n is the variable, which is the natural numbers, and that has a starting place of 1. So that means I want you to plug in 1, 2, 3, 4, and 5. Okay, so I want the first 5 terms. That's not ambiguous, and terms is just a fancy word for outputs when we talk about sequences. And so what does a sequence look like? Let's just look at some examples. Maybe it's a function on natural numbers, and maybe the function is defined as a sub n equals something, right? Just like f of x equals or g of x equals. Maybe a sub n equals 2 to the n over n plus 1. It's just a function on the natural numbers, just like you would have f of x, g of x, or h of x. It's just a little bit different looking notation to kind of emphasize the fact that we're dealing with a different type of function, a more discrete function. And if I ask the first 5 terms, we would just be plugging in 1, 2, 3, 4, and 5. So we would denote it as a sub 1 instead of a of 1, right? Like f of 1 or g of 1. So a sub 1, so the first term of the sequence. A sub 2, A sub 3, A sub 4, A sub 5. I'm saying sub because subscript, so A sub 5. These would be the first 5 outputs of this function. How do I find them? Well, it's just a function. I'm replacing n with 1. I'm replacing n with 2. Replacing n with 3. So I treat it just like finding outputs of functions. So no calculus is involved at this step, right? It's just some algebra, which is why you introduce sequences early on in math. So if I plug in 1, 2 to the 1, right? 1 is the exponent up here, is 2. 1 plus 1 is 2, so we get 2 over 2, which reduces to 1. If I plug in 2, we get 4 in the numerator, 2 squared. We get 2 plus 1, which is 3 in the denominator, so we get 4 thirds. If we plug 3 in, we get 2 cubed now, which is 8, right? So you notice the numerator is powers of 2. So we get 8 over 3 plus 1, which is 4, right? So 8 over 4, which simplifies to 2. If I plug 4 in, we get 2 to the 4th, which is now 16. And 4 plus 1 is 5 in the bottom, so we get 16 over 5. And finally, plugging in 5, we would get 2 to the 5th, which is now 32. And then we get 5 plus 1, which is 6. So we get 32 over 6. Which 6 doesn't divide into 32, but we can reduce it if we want. This would be divided with everything by 2, 16 thirds. If I wanted to reduce it. And of course, we understand I only want the first 5 terms, but there is actually no end to this sequence. There's no last term to plug in because the natural numbers are infinite in nature, right? We go on forever. And so if we wanted to start a list of all the outputs, right? A listing maybe, we put parentheses like, or these nice fancy brackets. And what have we got so far? The first term was 1, and then 4 thirds, and then 2, and then 16 fifths, and then 16 thirds, and dot, 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 right? It would continue on forever, right? It does not have an end to it. Sequences are infinite. But we just wanted the first 5 terms. Now there is a definitive starting term, and we can continue on. The nice thing about sequences or functions on the natural number, which we call sequences, since the natural numbers are just our counting numbers, there is nothing between the output 1 and the output 4 thirds, right? There's nothing to plug in between 1 and 2. The first natural number is 1. You don't plug in 1/2, 1.5. You don't plug in 1 3/4. You don't plug in 1.9. That does not exist for these functions. That is not within the domain, and so the next number is 2. Meaning, if I wanted to look at a picture or a graph of this function, just look at what it looks like. Well, my inputs along the x-axis or just the natural numbers. There's nothing in between. In fact, I'll start at 1. And the output at 1 was 1. I won't draw it to scale, just so we can visualize a little better. The output for 2 was 4 thirds, which is 1 1/3, so a little bit bigger than 1. The output for 3 was 2. The output for 4 was 16/5, which is, if you put that in calculus, a little bit bigger than 3. And finally, the output for 5, we got 16/3, which is a little bit bigger than, what, 5, right? So out of the picture, 4, 5, it's way up here. And we look at these dots, it looks like it's getting larger, right? We see that it's growing. And, well, we're not sure if it's continuing to grow, but it looks like it's growing. Now, it's very important. This is a function on the natural number, so what you would like to do in calculus is like, okay, I graph some points, I connect them with a nice continuous line because it's assumed, oh, well, yeah, you can plug in all the numbers between 1 and 2, all the numbers between 2 and 3, they would have outputs, and we would connect the dots and make a nice continuous curve with all of these points. But there actually is nothing to connect here, right? That's it. It's just a collection of dots in the plane. I bring this up because now calculus becomes a little bit interesting. How do you talk about tangent lines and areas? You really can't. Right? The calculus in terms of derivatives and integrals doesn't apply to sequences. We can't be doing that with sequences. So how does calculus come into play? We'll take a look at that. There's an idea of what a sequence might look like. You can have all sorts of things for the outputs of sequences. Notice, right, we have fractions here. I could say the square root of n, or e to the n, or pi to the n, right? It doesn't matter what the outputs of the sequence are. It's only that the inputs are restricted to the natural numbers. So the nice thing about sequences, since the inputs are restrictive, and I'm only allowed to plug in natural numbers, this allows me to now define some new types of functions. Functions that you didn't encounter in continuous version of calculus, right? Continuous calculus, continuous functions. But that you can encounter when we talk about sequences. And so let's take a look at what maybe some of that might be. All right, so first let's take a look at introducing something like this. -1 to the n times 3 to the n. So let's take a look at this sequence. So both are exponential, -1 to the n times 3 to the n. And let's again look at the first, we'll just look at the first 4 terms. Just to give you an idea what's going on. So that means I want A1, A2, A3, and A4. I want the outputs when you plug in 1, 2, 3, and 4. So I treat it just like a function, right? There's no calculus involved. I'm just plugging in numbers, plugging in 1, 2, 3, and 4. And let's just see, -1 to the 1 times 3 to the 1. -1 squared times 3 squared. -1 cubed times 3 cubed. And -1 to the 4th times 3 to the 4th. Now the second term is just going through powers of 3. And so let's just look at the powers of 3. We get 3, 9, 27, and 81. Those are looking at powers of 3. 3 to the 4th, 3 cubed, 3 squared, and 3 to the 1. Now what's interesting is, what about this -1 to the n? What does this do to my terms? And we're going to see something interesting. Okay, so -1 to the 1 is -1. And -1 times 3 is -3. So that outputs -3. -1 squared, well, that's just -1 times -1, which is still 1, but now +1. And so now I take 9 and multiply by 1, which actually just leaves it as 9. So you see, so far it hasn't changed this number, it's just changed its sign. What about -1 cubed? Well, that's -1 times -1 times -1, which is now 1 times -1, which is back to -1, right? So it's not a number outside of 1, it's either 1 or -1. And if it's an odd power, it's going to be negative. Negative times negative times negative is negative. Well, and 1 times 1 times 1 is still 1. And so the only contribution here, it's not changing this number, it's just making it -27. And if you see the pattern here, then -1 to the 4th is now +1. 1 times 3 to the 4th is just 81. So it's not changing the number, it's just changing its sign. And so we would say a term like this is going to alternate this sequence. It's going to alternate sign, that is its contribution. It's not changing the value of the number, it's just alternating the sign of the number. It's making it either negative or positive depending on n, the exponent, whether it's odd or even. Now, why do I bring this up in sequences? You actually can't address this type of continuous function. If I replace n with x, this would be a big issue. Why? Because if we're continuous now, that means I can plug in possibly fractions and all these kinds of things. Well, if I let n be 1/2, that would be a big issue, because then you'd be taking the square root of -1, which is a complex number, it's not a real number. And we're only dealing in real valued calculus, and so we don't like that. And so we wouldn't consider this. And so exponential functions, if you think back, this is an exponential. Exponential functions have to have a positive base. And this has a negative one. So it's not introduced in continuous functions, but it can be introduced with sequences. Since I'm only plugging in natural numbers, there's nothing wrong with -1 to the n. So it alternates the sign. We can also introduce another type of operation with sequences that you don't deal with continuous functions on the real line, and that is what we call a factorial. So if you've ever taken a statistics class, you've been introduced to factorials before. You might have been introduced to factorials before calculus as well, and maybe algebra or trig or pre-calc. Factorials is an operation, and it's an operation on the natural numbers. So that's why this works. This is an operation on the natural numbers. Now, not to scare you, but there is actually a continuous version of factorials, the gamma function, which, if you're an engineering student, you might deal with at some point in your career, in your college career. But for right now, factorials, we're only dealing with the natural number operation, which we denote by an exclamation point. It's not because we're really excited about it, but it is because the number gets very large. N factorial, what is it? Is defined to be, you notice we're using the letter n because it's natural numbers, is defined to be a product of natural numbers starting at 1 all the way up until whatever n is. So 1 times 2 times 3 times 4, all the way up till wherever we're told to stop, whatever n is. And so example, right? So 3 factorial would be 1 times 2 times 3, which is 6. So 3 factorial is 6. 4 factorial, well, 4 factorial would technically be 4 times bigger than this number, right? Because you take this and multiply by 4. It's 1 times 2 times 3 now times 4. And so what is 4 factorial? 6 times 4, 24. What is 5 factorial? Well, 5 factorial would be 5 times bigger than 4 factorial, because it's 4 factorial now times 5. And so really we would need to do 24 times 5. Or you can combine multiplication anytime, any way you want. If you don't want to think about 4 factorial, you can also think about, well, times 1 doesn't do anything. 3 times 2 is 6. 4 times 5 is 20. And 20 times 6 is 120. This number gets very large very fast. 6 factorial is 6 times bigger than this, actually 720. 6 times bigger than 5 factorial, ... And so factorials are very large, and it's defined on the natural numbers, right? So it's the natural numbers of 1 times 2 times 3, all the way up until n, right? So it's defined on the natural numbers. There's one exception with factorials. There is a special factorial, 0 factorial. Technically, 0 is not a natural number. It's included in our definition of factorial. If you ever encounter a 0 factorial, it has a special definition. It's defined to be 1. All right, so we don't freak out with 0. Any other natural number factorial is fine, 1, 2, 3, so on. 0 factorial, though, technically shouldn't be included. It's not a natural number, but we do, and if we ever encounter it, special definition, 0 factorial is 1. Now, while factorials are scary because they get very large very fast, say I define a sequence to look like this. Say it was n factorial over n plus 1 factorial. Say I had a factorial divided by another factorial. N factorial over n plus 1 factorial. And say I wanted the first 5 terms. That means I want A1, A2, A3, A4, and A5. The outputs of this function when you plug in the natural number 1, 2, 3, 4, and 5. And since factorials are functions defined on natural numbers, this is okay, right? We're going to be able to find out what these numbers are. And so what would a1 be? That would be 1 factorial over 2 factorial. And 2 factorial over 3 factorial. 3 factorial over 4 factorial. 4 factorial over 5 factorial. And 5 factorial over 6 factorial. And while you could figure out what each one of these numbers is individually and divide them by each other, there's an easy way to evaluate these. Let's look, for example, at 4 factorial over 5 factorial. I could find out these numbers separately and do 24 divided by 120. But I know the answer is going to be 5, 1 over 5. Why do I know this? If I just write out the definition of factorial, what that 5 exclamation mark and 4 exclamation mark mean, I get a fraction of a product in the numerator and an ascending product in the denominator. Now, the beautiful thing about fractions is you can cancel common factors. Factors means multiplication. So any common multiplications I have, I can cancel. Well, a factorial over factorial is going to have a lot of common multiplications. In fact, 1 through 4, they all share. The only difference is 5 factorial has the extra times 5 in the denominator. So all of these numbers reduce to 1, 1 over 1, 2 over 2, 3 over 3, 4 over 4. And the only thing left I have is a 5 in the bottom. This reduces to 1 over 5. So 4 factorial over 5 factorial is 1 over 5. What about 5 factorial over 6 factorial? Same kind of thing. Here we have 1 times 2 times 3 times 4 times 5. And in the bottom, 1 times 2 times 3 times 4 times 5 times 6. The only difference is now the 2's cancel, 3's cancels, 4's cancels, 5 cancels, and I have an extra 6 in the denominator that doesn't reduce with anything. So what am I left with? 1 over 6. If I follow that same pattern, 3 factorial over 4 factorial is 1 over 4, 1 over 3, and 1 over 2. In fact, in general, 1 times 2 times ... up till n, that would be the definition of n factorial. The definition of n plus 1 factorial is, well, hey, you're going to go all the way up till n, and then 1 more, n plus 1, the next natural number. And so what's going to happen every time now is all of these numbers will cancel up until n, and all you will be left with is whatever n plus 1 is in the denominator. So if it's 1, then you have 1 over 2. A2, 1 over 3. A3, 1 over 4. A4, 1 over 5. A5, 1 over 6. And so they all reduce, right? If we write out some terms, we can see the sequence and so on. And so factorials over factorials are oftentimes okay to deal with, right? They don't scare us too much because there can be some simplification. But like I said again, factorials is something else we can introduce when we talk about sequences. There's one more thing that we can introduce before we end this video. And the last thing that we're going to introduce is what we call a recursive sequence. So this isn't a new operation, it's just kind of a weird way of talking about sequences. A recursive sequence means the output of the following terms are dependent on the ones before it. So what do I mean by that? What I mean is I have to give you first something to work with, otherwise a recursive sequence, you don't have anywhere to start. So say I tell you that A1 is 2. I tell you the first output of this sequence is 2. Okay, well then n plus 1, I'll say, is 2a sub n plus 3. How did I define this function? Well, I gave you the first term, a1 is 2. And what does this mean? This means an plus 1. So the n plus 1th term in the sequence, what is it equal to? What is it defined as? Well, it depends on the nth term, right? The one right before it. What is it? It's 2 times the nth output plus 3. So if I just look at this for a second, if n is 1, then that means a2 is 2 times a1 plus 3. And a3 is 2 times a2 plus 3. a4 is 2 times a3 plus 3. And a5 would be 2 times a4 plus 3. So the outputs depend on the ones before. We can define in all sorts of ways. I can make it depend on the first two outputs before it. I give you some more information and so on, right? The point of recursive is that the next output depends on the ones before it in some way. And this is the way that I defined it. So how do I find the second output? Well, that would require knowledge of the first one. And that's why I have to give you something to start with. Well, since you know A1, that means this is 2 times 2 plus 3, which is now 7. 4 plus 3. To know A3, you need to know A2. Well, great, you just found A2 was 7, and so now it's 2 times 7 plus 3, which is 14 plus 3, 17. To find A4, you need to know A3. Well, great, you just found it. So 2 times 17 plus 3. So 17 times 2 is 34. 34 plus 3 is 37. And then finally, right, to get A5, we need to know A4, which we just found. So 2 times 37 plus 3. So we have 74 plus 3, or 77. And so these are the outputs of this sequence. Now they're recursively defined, right? The output of one depends on the outputs before. And so this is what we're introducing here, what we're kind of reminding ourselves of with sequences, functions on the natural numbers. We may have been introduced to them at some point in your math career before this class, but just kind of refreshing ourselves. The notation we deal with, some interesting things we can now incorporate with sequences, like alternating signs, that negative one at the end thing, factorials, recursive sequences. And none of this really involves calculus at this point. This is just kind of reminding ourselves what a sequence is. And what we're really concerned with now is, okay, remember that natural numbers never end. They go on forever. And so I could continue to list outputs of these sequences forever. There is no stop. It's not like I stop at the 5th term. The 6th term depends on the 5th term, and we can continue on forever. Where it becomes interesting, or where calculus comes into play now, is to answer ourselves the question of what happens if we let n go off to infinity. Let's take the limit as n goes off to infinity and see what happens to the outputs of my sequence. Are the outputs, or the terms, approaching anything? If you look at this sequence, for example, and you start to list out the terms, you get 1/2, 1/3, 1/4, 1/5, ... And if you start to inspect this, you're like, wait a minute, it looks like these terms are getting smaller. And as I continue to plug in larger and larger natural numbers, I'm going to get smaller and smaller terms for this sequence. And in fact, it looks like the terms of this sequence are approaching 0. They're getting smaller and smaller and approaching 0. So some sequences may approach 0. They may approach some other number. They may blow up. They may not approach anything at all. But that's the question that we need to ask ourselves. And that's where calculus is now going to come into play. And so in the next video, we're going to look at sequences, but now through the eyes of calculus. And what we're going to consider is what happens when we let n go off to infinity. Let's go to the end of the natural numbers and see if the outputs of my sequence, or the terms, go to anything specific. Do they approach a certain value? And so we're going to incorporate limits. So in the next video, we're going to look at sequences through the lens of calculus.